Hi, I'm Brian Walton, and this is a presentation on differentiability. Derivatives are a function that allow us to compute the rate of change for a given function f of x at any point x. The rate of change is the slope of the tangent line. Now on the graph that you see below in purple, we have a function. If I think about the function, at the value x equals 1, the height of the function is 1. That's what it means to say f of 1 equals 1. I also have drawn the tangent line, which is blue. If I calculate the slope of the tangent line by looking at the rise and the run, delta y is 2, delta x is 1, and so the slope of this tangent line is 2. We say f prime of 1 equals 2. The derivative of my function at x equals 1 is 2. However, the definition of the derivative is in terms of the limit of the average rate of change as I think about a second point, which is illustrated in this movie by the red point, as it approaches the first point. So if I were to calculate the slope for all of these different points, which I'm calling z, I would get a graph, or I get another function. The derivative is the limit as I think about that second point getting close to 1. Notice as that second point, z, gets close to the blue point at 1, the red line is very close to the blue line. And so the derivative happens to be the limit of that slope, which again we see is 2. Now the derivative is only defined where that limit has a value. So we say that my function f is differentiable at a point only when the derivative exists at that point, when the limit exists at that point. Otherwise we say my function is non-differentiable. The rest of this slide presentation is talking about possible causes for non-differentiability. We'll think of three basic categories. First, if the function itself does not exist, in other words, if c is not in the domain of the original function, I can't very well talk about a tangent line because there's not even a point to talk about. This presentation will not illustrate any examples of this until the very end. The second possibility is the function itself exists, so c is in the domain, but my function is not continuous. We'll have two different types of discontinuities illustrated in this presentation. One is where there is a single point out of place. The second we'll look at is a jump discontinuity. There are other types of discontinuities that are not illustrated in this presentation, and at each of those, again, our function will not be differentiable. Third, it's possible that my function is continuous, but that the limit of my average rate of change itself has no limit. This first example illustrates a function which has a removable discontinuity. At x equals 1, we see a point that is above the graph that we would expect to fill in at the purple hole at x equals 1. The actual value of the function is 2. The point that we would expect it to have been is at a height of 1. When I calculate my derivative, I have 2 points. First, I consider my point of interest at x equals 1. That's where I'm calculating a derivative. The second point is the moving point, which I'm going to think of as z. This second point moves closer and closer to 1, and we want to calculate what happens to the slope of the line going from the red point at z to the fixed point, blue. If I think about what's happening to that slope, I can see that there's a variety of different possibilities. As z gets close to 1, you can see that my function of my average rate of change has no limit at z equals 1. And so we say my derivative doesn't exist. Notice, by the way, that the red line joining my z point and my x point, the secant line, when it gets close to 1, my line is almost vertical. So if I'm thinking about the left side, whenever the red point is to the left of 1, I can see that my slope is positive and is getting steeper as I get close to 1. That's illustrated in the graph below by the vertical asymptote that's going up to positive infinity. So we say the derivative calculated from the left goes to positive infinity. It's not defined. If I think about the right side, as z approaches from the right, again, the graph is getting steeper, but all of my slopes are negative, and I can see on the graph below the slope of the average rate of change, or the slope of the secant line, is going to negative infinity as z approaches 1 from the right. And so when there's this type of discontinuity, a removable discontinuity, my derivative does not exist. In this second example, we have a jump discontinuity. We see it's a jump discontinuity because the limit from the left and the limit from the right of my function are different. If x approaches 1 from the left, my function has a limit of 1.5, the top piece of my function. If x approaches 1 from the right, my function has a limit of negative 1.5, the bottom branch. Because these two limits are different, I have a jump discontinuity. In the current example, f of 1 is equal to 0. That's the point on the axis. So if I were to try to calculate the slope of the tangent line at x equals 1, first of all, there is no tangent line. There's no piece of the function that's actually touching my point at 1, 0. Let's see what happens if I think about the definition of the derivative. The definition of the derivative says what's the limit of the slope of the secant line as the point off of x equals 1, illustrated in red, gets closer and closer to 1. Notice in this case, regardless of whether I'm approaching from the left or from the right, my secant line is becoming more and more vertical. My slope is becoming infinitely negative. It's negative because you can see my line is always down and to the right. So here's a graph. If I were to graph the slope of the secant line as a function of my second point z, the red point, you can see that as z approaches 1, both sides from the left and from the right are going to minus infinity. Now this is always going to happen. If I were to calculate the limit from the left, which is what we would call the left derivative, if I calculate the limit from the left of the slope of the secant line, f of z gets closer and closer to 1.5, the top branch. If I let c represent the value of f of 1, then the top of my slope is 1.5 minus c. The bottom is going to 0. But because z is less than 1, z minus 1 is always a small negative number. So this limit only has a chance of existing if c, f of 1, is equal to 1.5. That would correspond to moving my point up and filling in the circle at 1, 1.5. On the other hand, my right branch has a limit f of z minus f of 1. The right limit for f of z was negative 1.5. And so the only way that this limit exists is if my point is at the bottom point at negative 1.5. So it's impossible for both of these limits to exist at the same time. If I move it to the top, yes, the limit on the left now exists. So in this case, you can see that the limit on the left is 0. And so that corresponds to noticing that my z coming from the left looks like a nice tangent line. On the other hand, when I approach from the right, you can see that my slope is going to negative infinity. The graph below that shows the slope of the secant line, you can see has a vertical asymptote on the right that's going down to negative infinity. And so we would say the limit from the left at 1 is 0, but the limit from the right doesn't exist. We have a left derivative. If I go from the right, you can see that this time the right limit exists. And so we would say the right derivative at 1 is 2. But notice now, by moving the point down to negative 1.5, the left derivative no longer exists. The left limit, as z approaches 1 from the left, is now going to negative infinity. So the problem with a jump discontinuity is that regardless of where you put the point f of x, the point of interest, it's impossible to satisfy both the left and the right at the same time, and so it's going to be impossible to have a derivative. So we've looked at some cases where we are discontinuous and we saw that in all cases where we're not continuous, we do not have a derivative. This example takes a look at a function that is continuous, but still is not differentiable. So notice that this piecewise function, which is basically two parabolas glued together at x equals 1, is continuous. The value of f of 1 is 1, and the limit from the left and the right are both 1 as well. And so this function is nice and continuous. But let's see what happens if I try to think about the derivative. If I calculate the slope of the secant line and think about how does that depend on the location of z, notice that from the left I have one line that has a positive slope, but if I'm coming from the right, I have a negative slope. So if I were to calculate the derivative on the left, which I've illustrated with a tangent line that's coming from my point to the left, that tangent line has a slope of 2. This corresponds to the fact that the slope of my secant line has a limit of 2 as z approaches 1 from the left. And so we say we have a left derivative with a value of 2. On the other hand, if I think about the right branch, as z approaches 1 from the right, we can see that we get a different tangent line. The slope of that tangent line is negative 2, which corresponds to the limit from the right as z approaches 1 from the right. The slope of my secant line has a value of negative 2. So because I have different slopes from the left and the right, the derivative itself does not exist. There is no single tangent line at x equals 1 that describes both the left and the right. So whenever the function is not smooth, if it has a corner, which we call a node, or if there's any sort of non-smoothness, my function will not have a derivative at that point. So let's summarize what we've learned. We say a function is differentiable if it has a derivative at a point. So a function is differentiable at a point means that first, the function itself has a point. F of a is defined. Or in other words, a is in the domain. Second of all, I need to have a tangent line. And third, the slope of the tangent line needs to be a definite number. The only ways that can happen are if the function is continuous and smooth. If my function is not continuous, I cannot be differentiable. We saw that with a removable discontinuity. We also saw it with a jump discontinuity. In either case, if I thought about the slope of the secant line, I'm going to have an infinite limit, and so I cannot be differentiable. The second case that we looked at was where we were continuous, but not smooth. This was when the slope had a corner. The function had a corner. Anytime the function is continuous, but it's not smooth at a point, for example, the corner, again, that's not differentiable. And so anytime we know that a function is differentiable, we know that the original function must have been continuous and smooth. So let's take a look at some examples of functions and see if it's differentiable at various points. Here's our first example. This function is a line that's been chopped into pieces and just sort of glued next to each other. So if I thought about where is this function differentiable and where is it not differentiable, you should notice that every time the function has a break, it cannot be differentiable. Here's a graph of the derivative. Notice that because my original function is made up of a bunch of lines, the slope is the same everywhere. My slope is 2. But every time my function above, the original function, has a break, the derivative is not defined. So this function was non-differentiable at each of the integers because my function had breaks. So here's another function to consider. There are a variety of points that are of interest. We'll go through them one at a time. At this first point, we see that our function has a removable discontinuity. It's defined, so my function f of 1 has a value, but the value does not agree with the limit, and so it's impossible to have a derivative. Notice there's a hole in the graph of my derivative. If I were to move that point down and filled in the hole, so I changed my function, I would fill in that dot in the derivative. The second point of interest is at this jump discontinuity. Notice that my function is defined so that I have a right limit agreeing with the function. In other words, my function is right continuous, but it's not left continuous. Because of the jump discontinuity, my function is non-differentiable at this point. At this point, I have a corner, and so again, I have a non-differentiable point. The original function is continuous, but it's not smooth, and so I don't have a derivative. Notice, by the way, that the derivative has a jump discontinuity at both x equals 0 and at x equals 2. If I look at a jump discontinuity in the derivative, I don't know the cause of that discontinuity. It could have been from a discontinuity in the original function, or it could just correspond to a corner. This third point, my function does not have a derivative because the original function is not even defined. Now, if I thought about the left derivative, what's the slope if I approach from the left? Notice that at x equals 2, I could now fill in the point. My slope from the left is, approximately negative 1 point, I can't tell what that is, some negative number. In other words, my derivative from the left has a value, but the derivative at the jump discontinuity at x equals 0 is not filled in. That's because if I thought about approaching 0 from the left, if I imagine a second point going to the point up above at x equals 0, as my second point approaches z equals 0, my slope would become vertical. So even a left derivative is undefined at x equals 0. If I thought about the right derivative, on the other hand, both x equals 0 and x equals 2 now get values. That's because if I approach from the right, both of those 2 points have nice slopes. But the original derivative is undefined at those points. So those are our examples. A function is differentiable means I have a nice tangent line, and I can calculate its slope. If I'm undefined, or discontinuous, or not smooth, I don't have a good tangent line that I can calculate its slope, and so I'm not differentiable.